Now we are looking into the first chapter of Signals and Systems, which is Introduction to Signals and Systems. So, as a part of this chapter, we will be mainly looking into basics of signals, which and we will also be looking into the classifications of the signals. Then we will be looking into the characterization of the systems. First, we will look into the definition of the signal. A signal is defined as a some a signal is defined as a function which conveys some useful information, and it is also defined as physical variation of one quantity with respect to other. So if we take the examples of the signals, the speech signal is an example of a signal which can typically be written as f of t. The image is also an example of the signal, which can be written as f of x comma y. Similarly, video signal is also a example of the signal. Now we will look into the definition of the system. A system is defined as an entity which extracts some useful information from the signal, or it processes the signal. So example of the system is a filter implemented to process a speech signal. Given the idea about the basics definition of the signals and system, now we will look into the classification of the signals. Based on the quantity under consideration, we can classify signals in different ways. The first classification we will be looking into is continuous time versus discrete time signals. In case of continuous time signals, the signal is defined at all instants of time. Whereas in case of discrete time signals, the signal is defined only at specific instants of time. So given a continuous time signal, we can get the discrete time signal by sampling. So, so suppose if you take any continuous time signal, it can be written as x of t. Then the discrete time signal x of n can be written as x of t, which is at a specific instant t is equal to nt, where n belongs to z. So in the figure shown, we have a continuous time signal which is x of t. From this, we can obtain the discrete time signal x of n by sampling. So here the points marked corresponds to x of n, that is they corresponds to some integer instance nt. Similarly, another classification of the signals is conjugate symmetric versus skew symmetric signals. A signal is defined as conjugate signal if x of t is equal to x star of minus t, where the star operation is conjugation. Similarly, the signal is defined as conjugate skew symmetric if x of t is equal to minus x star of minus t. Similarly, in case of discrete time signals, the conjugate symmetric definition is modified as x of n is equal to x star of minus n, and conjugate skew symmetric definition is modified to x of n is equal to minus x star of minus n. So under the section conjugate symmetric and skew symmetric property, we will be mainly looking into the different properties as related to continuous time signals, but they can equivalently analog they can equivalently be applied for discrete time signals as well. Given the idea about conjugate symmetric and conjugate geosymmetric signals, now we will look into a specific property of any arbitrary signal, which is as given. Given any arbitrary signal x of t can be written as the sum of two signals xe of t and xo of t, where xe of t is conjugate symmetric part of the signal x of t and xo of t is conjugate skew symmetric part of the signal x of t. Here xe of t can be written as x of t plus x star of minus t divided by 2, and xo of t is equal to x of t minus x star of minus t divided by 2. It can also be written that the conjugate symmetric part of the signal xe of t is conjugate symmetric. Hence, if you find xe star of minus t, it can be written as x of minus t, x star of minus t plus x of t divided by 2. This is by doing the time reversal and conjugation operations on xe of t given here. This is equal to xe of t signal, xe of t itself. So this is the conjugate symmetric part of the signal. Similarly, we can write xo star of minus t is equal to x star of minus t minus x of t divided by 2. This is equal to minus xo of t. This is obtained by doing the conjugation and time reversal operations on xo of t given here. So xo of t is conjugate skew symmetric. From this we see that any signal x of t can be written as sum of two signals, of which the signal 1 is conjugate symmetric and signal 2 is conjugate skew symmetric. Now let us consider an example. So let us say, suppose the function x of t is given as shown. Now we have to find the if the signal x of t is conjugate symmetric. We know that the signal x of t is conjugate symmetric if it satisfies the condition x star of minus t is equal to x of t. The given signal x of t is real, so x star of t is equal to x of t, and also from the given signal we can see that x star of minus t is equal to x of minus t is equal to x of t. So the signal x of t is conjugate symmetric. And also we can write that in case of real signals, the conjugate symmetric property boils down to even property, and the conjugate skew symmetric property boils down to odd property of the signals. Now we look into some of the salient notes related to these properties. If the signal, let us consider two signals xe1 of t and xe2 of t, which are conjugate symmetric, and xo1 of t and xo2 of t, which are conjugate skew symmetric. From this we can list down the following properties. xq1 of t plus xq2 of t would be conjugate symmetric if the signals xe1 of t and xe2 of t are conjugate symmetric individually. Similarly, xo1 of t plus xo2 of t would be conjugate skew symmetric, and xe1 of t multiplied by xe2 of t would be conjugate symmetric, and xo1 of t multiplied by xo2 of t would be conjugate symmetric. So, given two signals which are either conjugate symmetric or conjugate skew symmetric, we can apply different operations on the signal and can deduce the conjugate symmetry or skew symmetric properties from the given salient points. Now, let us look into some of the problems related to continuous time versus discrete time signals. Consider a signal x of t is equal to sine pi by 3t, where t belongs to r means set of real numbers. We have to find if the signal is continuous time or discrete time. We know that a signal is continuous time signal if it is defined for all instants of time, that is t. So t should belong to r, and also we should know that the signal is called discrete time signal if the signal is defined only at a specific values of independent variable. But here the signal x of t is equal to sine pi by 3t, and t belongs to r. So the signal is defined for all instants of time t belongs to r. So the signal is continuous time signal. Now similarly we will consider another signal y of n is equal to cos pi by 3, correct, cos pi by 6n. Here n belongs to z. We have to find if the signal is continuous time or discrete time. By the nature of the signal, y of n is defined only at specific instance of time, that is for n belongs to z. So the signal y of n is discrete time signal. Now let us start looking into some of the problems related to conjugate symmetric versus conjugate skew symmetric signals. Consider a signal x of t is equal to t multiplied by u of t minus u of t minus t. We have to find the conjugate symmetric and conjugate skew symmetric parts of the signal. We know that u of t is equal to 1 for t greater than or equal to 0, 0 otherwise. So here u of t means it's a unit step function. We know that the conjugate symmetric part of the signal xe of t is given as x of t plus x star of minus t divided by 2. This can be obtained if we find out x star of minus t. From the given signal x of t, x star of minus t can be written as minus t, sorry, x star of t can be written as t into u of t minus u of t minus t, because the signal x of t is real. From this, x star of minus t can be written as minus t multiplied by u of minus t plus u of minus t minus t. From this, we can find out conjugate symmetric part of the signal xe of t as half multiplied by t into u of t minus t into u of t minus t. This should be added with x star of minus t. So minus t into u of minus t minus t multiplied by u of minus t minus capital T. So this is the conjugate symmetric part of the signal. Similarly, conjugate skew symmetric part of the signal xo of t can be written as x of t minus x star of minus t divided by 2. Upon substitution, this can be written as half into t into u of t minus t into u of t minus capital T plus t into u of minus t minus t into u of minus t minus capital T. sorry, this should be minus, so this would become plus. So based upon this, these signs remain same. So we see that the conjugate symmetric part of the signal is this, and the conjugate skew symmetric part of the signal is this. So given any signal x of t, the conjugate symmetric and conjugate skew symmetric parts of the signal can be obtained as above. Given a signal x of t is equal to u of t minus u of t minus capital T, we have to find its conjugate symmetric and skew symmetric parts in terms of a function rect of t1 comma t2, which is as shown. We know that the given signal x of t is equal to u of t minus u of t minus capital T can be written as rect of 0 comma capital T, and also x of minus t can be written as u of minus t minus u of minus t comma sorry minus capital T, which is equal to rect of minus t comma 0. So x star of minus t will also be equal to rect of minus t comma 0. From this, the conjugate symmetric part of the signal xe of t is given as half multiplied by x of t plus x star of minus t. This is equal to half multiplied by rect of 0 comma t plus rect of minus t comma 0. This will be equal to half multiplied by rect of minus t comma capital T. Similarly, the odd component of the signal or conjugate symmetric part of the real signal given becomes half multiplied by x of t minus x star of minus t. This upon simplification becomes half rect of 0 comma t minus rect of minus t comma 0. So for the given signal, the conjugate symmetric part and conjugate skew symmetric part in terms of the given rect function are as shown. Now there is a signal x of n given as 3 plus j comma 1 comma 3 minus j. Here the center point is at 1, means 1 corresponds to the instant n is equal to 0. We have to find the conjugate symmetric part and the conjugate skew symmetric parts of x of n. The conjugate symmetric part of x of n is given as xe of n is equal to half multiplied by x of n plus x star of minus n. Similarly, the odd component of signal xo of n is equal to half multiplied by x of n minus x star of minus n. As the given signal is complex, x star of n can be written as x star of n is equal to 3 minus j comma 1 comma 3 plus j, and from this x star of minus n can be written as 3 minus j comma 1 comma 3 plus j. So upon substitution we get the conjugate symmetric part of the signal as half multiplied by 3 plus j comma 1 comma 3 minus j. This is added with 3 minus j comma sorry 1 comma 3 plus j. This upon simplification becomes 3 comma 1 comma 3 with center point at 1. Similarly, the odd component of the signal is half multiplied by 3 plus j comma 1 comma 3 minus j minus 3 minus j comma 1 comma 3 plus j. From this, the odd component of the signal becomes j comma 0 comma minus j. So For the given x of n, the conjugate symmetric part is 3, 1, 3, and the conjugate skew symmetric part is j0 minus g. We can also see that if we add xe of n and xo of n, we get x of n back. We can also see that xe of n is conjugate symmetric as xe of n is equal to xq star of minus n, and also xo of n is conjugate skew symmetric as xo of n is equal to xo star of minus n. Consider a signal x of t is equal to 1 by 2 whole power t multiplied by u of t. We have to find the conjugate symmetric part of the signal x of t. We know that the conjugate symmetric part of the signal is given as half multiplied by x of t plus x star of t, sorry, x star of minus t. From this, we can see that we need to find out x star of minus t. As given x of t is real, x star of minus t is equal to x of minus t is equal to 1 by 2 whole power minus t u of minus t. So the conjugate symmetric part of the signal xc of t is equal to half multiplied by x of t, which is 1 by 2 whole power t u of t plus 2 power t u of minus t. So the given xc of the obtained xc of t is the conjugate symmetric part of the given signal. Now let us consider another problem. Here there is a discrete time signal x of n given. It is also given that the signal is conjugate symmetric. Then can we characterize anything about x of 0? So as the signal x of n is conjugate symmetric, x of n is equal to x star of minus n. So n is equal, we have to characterize about n is equal to 0. So upon putting n is equal to 0 in above relation, we get x of 0 is equal to x star of 0. This is the property of real numbers, because if a is real, we know that a star is equal to a. From this we see that as x star of 0 is equal to x of 0 is real. So this is what we can characterize about x of 0. Similarly, there is a signal x of n given. It is given that x of n is conjugate skew symmetric. Can we characterize anything about x of 0? As x of n is conjugate skew symmetric, x star of minus n is equal to minus x of n. So this is by the definition of the conjugate skew symmetric signal. Upon substituting n is equal to 0 in above relation, x star of 0 is equal to minus x of 0. This is the property of purely imaginary numbers, because we know that if b is purely imaginary, b star is equal to minus b. From this, we see that if x of n is conjugate skew symmetric, x of 0 is purely imaginary, or it could be 0 as the given relation is satisfied for 0 also. Now let us consider another problem. As per the problem, there is a signal x of t given as shown in the figure. Sorry, there is a signal x of t is equal to u of t is given. We need to find the conjugate symmetric and conjugate skew symmetric parts of x of t in terms of y of t, which is shown in the figure. We know that the conjugate symmetric part of the signal xc of t is given as, xc of t is given as half into x of t plus x star of minus t. Here x of t is u of t. As u of t is real, x star of t will be equal to u of t itself. So x star of minus t will be u of minus t. We know that this quantity is equal to 1, so the even part of the signal is half. Similarly, the odd component of the signal xo of t is given as half multiplied by x of t minus x star of minus t. This can be written as half into u of t minus u of minus t. We know that the given signal y of t can be written as half multiplied by u of t minus half multiplied by u of minus t. So upon simplification, we see that xo of t is y of t itself. So from this we see that the even component of the signal is half and the odd component of the signal is y of t itself. This is for the signal x of t is equal to, consider a signal x of n is equal to 2 plus 3j whole power mod n. We have to find if the signal is conjugate symmetric. We know that if the signal is conjugate symmetric, x of n should be equal to x star of minus n. For the given signal, we can write x star of n, which is the conjugate of x of n, is equal to 2 minus 3j whole power mod n. From this, x star of minus n is equal to 2 minus 3j whole power mod n. This is not equal to x of n for every n. From this, we see that x of n is not conjugate symmetric. Now consider another signal x of n as shown in the figure. Here the value of x of n at n is equal to 1, 2 and 3 are given as 1, and the values at the instant n is equal to minus 1, minus 2 and minus 3 are given as 1, 1 and a. It's given that x of n is even. Then we need to find the value of a. We know that if x of n is even, x star of minus n is equal to x of n for every n. From this, for n is equal to 3, x star of minus 3 is equal to x of 3. As x of n is real, x of minus 3 is equal to x of 3 is equal to 1. From this, a is equal to 1. Now consider another signal y of t as shown in the figure. Here the signal is present for the interval minus t to capital T, and it takes values in the range of a to minus a. We have to find if the signal is odd. We know that if the signal is odd, y of minus t is equal to minus y of t. This is the case as y of t belongs to R. From the given signal, we see that the relation y of t is equal to minus y of t is satisfied. So the given signal y of t is odd. Now consider another sequence x of n is equal to j comma 2, where the value of 2 corresponds to the instant n is equal to 0. We need to find the conjugate skew symmetric part of x of n. We know that the conjugate skew symmetric part xo of n is given as half multiplied by x of n minus x star of minus n. For the given x of n, x of minus n is equal to 2 comma j, where 2 corresponds to the instant n is equal to 0. From this, x star of minus n would be equal to 2 comma minus j. Upon substitution, we get xo of n as half multiplied by j comma 2 minus 2 comma minus j. Upon simplification, this becomes half multiplied by j comma 0 comma j. um, Sorry, so there is a mistake here. We know that the extra of minus n is given as 2 comma minus j. So uh, so this would be equal to, yeah, correct. So the odd component of the signal is given as half multiplied by j comma 0 comma j. So this is the conjugate skew symmetric part of the signal.